First of all, I would like to say thank you for the invitation to speak. It's a pleasure for me to give this talk. And this talk will be about a certain conjecture regarding the dimension of self-similar measures on the real line. And I'll start by giving the necessary definitions regarding self-similar sets and measures, then move on to describing the conjecture, and then move to describing recent development regarding it. So I'll start by talking about the self-similar sets. Throughout the talk, phi is a finite family of contracting similarities of the real line. And here lambda is a finite non-empty index set. And the numbers Ri, Ai are real numbers for every I, and the modulus of Ri is strictly between 0 and 1. And we call such a collection an iterated function system, or an IFS for short.
Ariel, excuse me?
Yes.
By similarities, you mean that the contractive factor is a scalar multiple of X?
Yes, yes. The maps are, these are the maps, phi I, and they takes a real number to Ri. The map phi I takes the real number X to Ri times X plus translation.
Because sometimes people talk about self-affine set, self-similar set.
Yeah, but on the line, the affine maps and similarities are the same. So
okay.
The one-dimensional case, it does not matter.
Thanks.
Yes. So it is well known that, but thank you for the question. It is well known that for such an non-empty compact subset K of R, which satisfies the following relation, this set K is equal to the union over I over its own images with respect to the maps in our IFS phi I. And this set is called the self-similar set, or the attractor, which corresponds to the IFS phi. Alternatively, K can also be characterized as the image of the coding map pi, which is a map from the symbolic space lambda to the power n into the real line. So the symbolic space, I mean the one-sided infinite sequences over the alphabet lambda. And this map pi takes such a sequence to this limit. When I do this with the mouse, you see, right? Yeah, okay. So this limit exists because the maps are strict contractions, and it's not very important. You don't need to remember this formula. I won't use the coding map much in the talk. So I'll move on to talking about the self-similar measures, which are the natural measures which are supported on self-similar sets. So suppose that we're also given a probability vector P, also indexed by lambda, which has strictly positive coordinates. Then there exists a unique Borel probability measure mu on the real line, which satisfies the following relation. Mu is equal to the average over I with weights pi of its own images with respect to the maps phi I from our IFS. So here phi I mu stands for the push forward of mu via phi I, which is defined as follows. So mu is called the self-similar measure corresponding to phi and p, and its support is equal to the self-similar set k. If I would not require that the probability vector has strictly positive coordinates, then the support would only be contained. But I will always require strictly positive probability vectors. And I'll describe a couple of different ways to characterize this measure. So first of all, directly from the fact that mu satisfies this relation, it follows that it is the unique stationary measure for the random walk on R, which moves from the point X to the point phi Ix with probability pi. This follows directly from this and from what it means to be such a stationary measure. And for the next characterization of mu, let p to the power n denote the Bernoulli measure on the symbolic space, which corresponds to p. So this is the unique probability measure on the symbolic space, which makes the coordinate projections IID random variables which are distributed according to P. And then it is easy to verify from the definitions that mu is equal to the push forward of the Bernoulli measure via the coding map I defined 2 slides ago. And for the last characterization, we say, which only holds in a specific situation, under an additional assumption, we say that the IFS phi is homogeneous if the contractions Ri, so these are the contractions of the maps Vi, are all equal to the same real number R, which is again has modulus between strictly between 0 and 1. In which case it is again easy to verify that the self-similar measure mu is equal to the distribution of this random sum, where the psi n's are IID random variables, which are distributed according to the translations AI and the probability vector P. So a well-known example of such self-similar measures which correspond to homogeneous function systems is the family of Bernoulli convolutions, mu R. It's a family of measures, so for every R between 0 and 1, there is such a measure. Mu R is defined as the law of this random variable, this infinite sum, where the plus minus signs are independent, unbiased random variables. So I will talk more about in greater detail about this family later on. It is been studied by many people since the work of Erdős in the 30s and even before, and I'll return to it later. So the computation of the dimension of self-similar measures is a basic and important problem in fractal geometry, and this will be the main topic of this talk. And before I move on to talking about the dimension of self-similar measures, I want to give the necessary definitions for the dimension of general measures on the real line, the things that we needed in this talk. So a Borel probability measure theta on R is said to be exact dimensional if there exists a non-negative number alpha, so that for theta almost every x, the following limit exists and is equal to alpha. Saying it differently, theta is exact dimensional if there exists such alpha, so that for theta almost every x, the theta measure of the interval around x with radius delta is equal to delta to the power alpha plus little o of 1 as delta goes to 0. So this number alpha describes the asymptotic decay rate of the theta measure of small balls around the theta typical points. So this number alpha, when it exists, it is called the dimension of theta and is denoted by din theta. And it is equal to the value given to theta by other commonly used notions of dimension. There are many notions of dimension of measures, and most of them are equal to this number din theta whenever this number exists. And in particular, this number is equal to the house of dimension of theta, which equals this quantity by definition. So the house of dimension of theta is defined to be the infimum of the house of dimension of all of the Borel subsets of the real line for which theta gives a positive mass. Okay, so now I'll move on to talking about specifically about the dimension of self-similar measures. So first of all, it has been proven by Fang and Hu in 2009 that self-similar...
Ariel, sorry, can you go back to the previous slide?
Yes, of course.
Suppose that we have a measure which is the sum of the Lebesgue measure on the unit interval,
yes,
and the Cantor measure on the classical middle
so
third
Cantor. It will not be exact dimensional in this case.
So it's not exact
you mean, for instance,
but it has a well-defined dimension according to the last.
Its house of dimension is certainly well defined, and in which case it will be the dimension of the Cantor Lebesgue measure. Right? You meant the Cantor Lebesgue plus Lebesgue.
So you mean that if a measure is exact dimensional,
Yeah.
then its dimension coincide with the Hausdorff dimension.
Yeah, precisely. The Hausdorff and the packing dimension, all kinds of definition. This is maybe the most familiar one, and this is the one I will need. So this is the
okay,
one.
but there are also non-exact dimensional measures which have a well-defined Hausdorff.
This quantity, the Hausdorff dimension of a measure, is always defined.
Okay.
This number is not always, but for nice dynamically defined measures, it usually is. Certainly, it's not a trivial statement. It's not an easy proof, but in 2009, they showed, Feng and Hu showed this, that for self-similar measures, also in higher dimensions, they are also always exact dimensional. And so if mu is a self-similar measure, this number d mu, I can talk about it, it's always well defined. And let me recall the definitions. So our notation, so phi is the IFS, so it's a finite collection of affine contractions of the line. P is a strictly positive probability vector. K is the attractor corresponding to phi, and mu is the self-similar measure which corresponds to phi and p. And note that since mu is supported on K, we always have these inequalities. So this inequality holds because mu gives a positive mass to K because it's supported on it, and because the d mu is equal to the Hausdorff dimension of mu. And this inequality holds because K is a subset of the real line, and so its dimension is at most 1. And so always the dimension of a self-similar measure on the line is bounded about by 1. And I'll say a couple of words regarding this inequality. So the original motivation to consider self-similar measures, the dimension of self-similar measures, is to compute the dimension, the Hausdorff dimension of self-similar sets. And in this situation, the upper bound for the dimension of self-similar sets is usually easy, and the challenging part of the problem is the bounding it from below, and this inequality shows why the dimension of self-similar measure is relevant.
So these two authors prove that self-similar measures are exact dimensional without saying what is the dimension? I mean... No,
you can't. Okay, they prove a nice formula in terms of certain conditional entropies, but not the number. They don't give the precise number.
Okay. So they give an algorithm how to compute it, but...
No, not an algorithm. They show that the dimension exists and it satisfies this formula, but they don't compute it.
So in concrete cases, it doesn't help you to...
Okay, so this shows that the value exists. You can talk about it. And in concrete cases, you need to do some different things in order to compute it. But actually, the fact that the exact dimension exists, it is used in the proofs. It used always in the proofs in order to compute the dimension explicitly.
Okay.
Yes. So I'll continue. So it turns out that the dimension of mu usually satisfies a certain formula in terms of P and Ri. So soon I will be more precise regarding what I mean by usually. So I now define this formula. So for this, let HP denote the entropy of the probability vector P, which is defined by this well-known formula for entropy of a probability vector. And let chi be the Lyapunov exponent corresponding to P in the inverses of the contractions, which is defined as follows. So this is the average over I with weights pi of the logarithms of the inverses of the modulus of the contractions. And this is always positive because the modulus of the Ri's is strictly between 0 and 1. And finally, we write dim S of phi and P for the entropy divided by the Lyapunov exponent, and call this number the similarity dimension of phi and P. So recall the similarity dimension of phi and P is the entropy of P divided by the Lyapunov exponent of P and the contractions. So it always holds that the dimension of mu is bounded above by the minimum of 1 and the similarity dimension. And moreover, there is an equality whenever the images of the attractor with respect to the maps in the IFS are disjoint. In which case, if these sets are disjoint, we say that the IFS phi satisfies the strong separation condition, or SSC for short. So when the strong separation condition holds, this is kind of the simple situation in which it is easy to compute the dimension and show that it satisfies this nice formula star. And a couple of words, the proof. So these facts.
In this case, the dimension does not depend on the probabilities, or it does depend on the probability?
It is, because the similarity dimension depends on the probability.
Under the separation condition?
Yeah, actually, under the separation condition, the dimension will be equal to this value, because if the strong separation condition holds, then this value will be strictly less than 1.
So the Hausdorff dimension of the support can be large. So
okay, this is the dimension of the measure, and if you want,
what's the relation between d mu and the dimension of the support of mu?
So there is a specific self-similar measure whose dimension is equal to the dimension of the support, and in order to compute the dimension of the support, you're looking at this measure, and this is why the analysis of self-similar measures give you the dimension of self-similar measures, give you the analysis of the dimension of self-similar sets.
No, I'm asking, well, maybe I will reformulate my question. Suppose that the strong separation condition satisfies, and suppose that the probabilities, so can you change the dimension of mu by changing the probabilities?
Yeah, of course, it will change, definitely. If you want to you need to, there is a specific self-similar measure which maximizes this quantity. And I wanted to concentrate on the dimension of measures in this talk, and so I didn't mention these things in order to get to the new.
Okay, because the contraction ratios are different for.
Yeah. But
okay.
Yeah. But also, if the system was homogeneous, the contraction was the same. Then in order to maximize, you need to select a probability vector with equal coordinates. It would also matter. And anyways, these facts follow directly from the fact that it's an easy exercise that follow directly from the fact that mu is the image of the Bernoulli measure. And since we have this, with respect to the Bernoulli measure, we have this asymptotics. And additionally to these facts, when the probability vector is and the contractions are fixed, this inequality star holds almost surely under a natural randomization of the translations. So by a natural randomization, I mean if the translations, for instance, if we have if the size of the index set is M, and we choose the translations according to the M-dimensional Lebesgue measure, then almost everywhere we will have this equality star. And there is an extra condition I should add that in order to otherwise this claim is not true. In order for this to be true, we need to require that all of the contractions have modulus strictly less than half. Otherwise, there are examples to show that this is false. And so this last claim, it was proven. This last result was proven by Polycott, by Jordan, Polycott, and Shimon in 2007. So given these facts, so by these facts, I mean the fact that this value is an upper bound for the dimension, that in the simple case of the strong separation condition, there is equality, and that under a natural randomization of the parameters, there is again equality. Given these facts, it's natural to look for as mild as possible an explicit condition which would imply this equality star. So the strong separation condition is an explicit condition, but it's very restrictive, and ideally we would not want the necessary and sufficient condition for this formula to hold. And ideally we would like some nice algebraic conditions in terms of the maps phi I. In the exact overlap conjecture, which I will now turn to, which I will soon state, provides such conditions. So I'll move on to talking about the conjecture. So note that first of all, note that there are situations in which it is obvious that there is a dimension drop. And by dimension drop, I mean that the equality star does not hold. and then we have this strict inequality.
Ariel, could you please remind the definition of dim SVP?
Yes,
I
dim
did
SVP
not
is
get
the
it.
entropy of the probability vector P divided by the Lyapunov exponent corresponding to corresponding to P and the inverses of the contractions, and the Lyapunov exponent is defined as follows. So dim SVP is this ratio.
Okay, thank you.
Yes. So as I said, there are situations in which it is obvious that the star does not hold, and then we have this inequality. So I'll describe the simplest situation in which such a thing can occur. So suppose that we know that the dimension of mu, the self-similar measure, is strictly less than 1, and that there are two disjoint indexes I and j in our index set for which phi I is equal to phi j. In which case there is a dimension drop. Why is this? Let me explain. Because we can throw from the function system phi the map phi j, for instance, and from the probability vector we can throw the jth coordinate and add it to the ith coordinate, and then we get a new IFS, a new probability vector. But the self-similar measure that will not change, and the Lyapunov exponent will not change, but the entropy will decrease strictly. And then the dimension of the self-similar measure will be bounded above by the new similarity dimension, which is strictly less than the old similarity dimension. And so we will have a dimension drop in this situation. And this is a special example of a more general phenomena that can lead to a dimension drop that I will now describe. So we say that the IFS phi has exact overlaps if there exists a positive integer n and distinct n words, I1 up to in and j1 up to jn in lambda to the power n, such that the corresponding compositions of maps from the IFS are equal. It's not hard to see that this is equivalent to saying that the maps in the IFS phi do not generate a free semigroup with respect to composition. By which I mean that there are two distinct words over lambda for which the corresponding compositions are equal. So the quality of these two definitions is an easy exercise which follows from the fact that the phi's are strict contractions. And it's also easy to see that there is a dimension drop. There is always a dimension drop if we know that the dimension of mu is strictly less than 1 and phi has exact overlaps. So recall, when I say that phi has exact overlaps, it means that the maps in phi do not generate a free semigroup. And the following Folcol conjecture, which is called the exact overlap conjecture, says that the reasons that I gave in the previous slide are the only one which can cause a dimension drop. So a version of it first appeared for sets in a paper of Karoli Shimon in the 90s. And the conjecture says the following: suppose that there is a dimension drop, by which I mean that this inequality holds, then phi has exact overlaps. So in recent years, this conjecture has been verified in various situations. And the first major development was achieved by Hochman in 2012. And now we will turn to talking about his result. So first of all,
Ariel, can I ask a question?
Yes.
Maybe there is not exact overlap, but maybe there are words, different words which approximate closer and closer, and maybe in this case.
So this is the
So why do you not expect a dimension drop in this? In such a
so in many situations, it has been shown that still the conjecture holds, but in general, this is the question. Yeah. So there are, I will say about it more, but you can show that you can have compositions which are close as you want, but you will still not have a dimension drop. I will soon, in a couple of slides, I will go give such a situation, and yeah, maybe it's a bit surprising, but this is the case. And the conjecture, anyways, predicts that the only reason for dimension drop is exact overlaps. And so Hochmann's Hochmann's result, it kind of prove a milder version of the conjecture, and I will now describe it. So I need some notation. So fix a norm on the vector space of affine maps from R into itself. And for every positive integer n, let delta n be the following quantity. Delta n is defined to be is defined as the minimal distance between two compositions of maps from our IFS, which correspond to two distinct n-words. Okay, so this is delta n, and note that there are exact overlaps if and only if there exists some n such that delta n is equal to 0, in which case from that n on, delta n will always be 0. And I define the following condition. So we say that the IFS phi is exponentially separated at infinitely many scales if there exists some positive epsilon, so that delta n is at least epsilon to the power n for infinitely many integers n.
The sequence delta n is not necessarily monotonic, monotonically decreasing?
It is because you can always yes, it always is monotonically decreasing. Yeah.
Oh, okay.
You can finish with the same, right? You can take n words and then obtain close n words and then obtain words of length n plus 1 by adding the same letter. Yeah.
I see.
So Hochmann's result, which proves a milder version of the just let me say regarding this condition. So this is a stronger requirement that saying that the map, the IFS phi has no exact overlaps. This is a stronger requirement than the absence of exact overlaps. And Hochmann's theorem, main theorem, says the following. If phi is exponentially separated at infinitely many scales, then there is no dimension drop. That is, we have this equality. So I'll mention two important corollaries of this result. So the first one verifies the exact overlap conjecture for systems defined by algebraic parameters. So it is not hard to see that if the contractions Ri and the translations AI are all algebraic numbers, and if we know that phi in this case has no exact overlaps, then phi is exponentially separated at all scales, by which I mean that there exists some epsilon so that delta n is at least epsilon to the power n for all n. So this epsilon will of course depend on the degree and height of these algebraic numbers. And the following corollary follows directly from this last observation together with Hochmann's theorem. So this corollary of course also appeared in Hochmann's paper. And it says that if the IFS has no exact overlaps and if all of the parameters Ri and AI are algebraic numbers, then there is no dimension drop. By which I mean that for any probability vector, the corresponding self-similar measure would have the correct dimension. I move on to the second corollary. So for for a real number t, we define the following function system, phi 1/3 t. So it's a system of three maps. It is homogeneous with contraction 1/3. This is why 1/3 appear in the notation. And the translations are 0, 1, and t. So I'm keeping the 1/3 denotation because later I will look at two parameter systems in which the contractions also varies. But for now the contraction 1/3 is fixed. And so by an observation, by an argument of Boris Solomiak and Pablo Shmerkin, which also appeared in Hochmann's paper from 2012, it follows that if t is such that the corresponding IFS phi 1/3 t is not exponentially separated at infinitely many scales, then it actually has exact overlaps. And the following corollary follows directly from Hochmann's theorem together with this last observation. And it verifies the conjecture of Furstenberg from the 70s. And the corollary says the following: the exact overlap conjecture holds for this family of function systems, phi 1/3 t, by which I mean that if t is such that the corresponding IFS has no exact overlaps, then there is no dimension drop. Let me just remark that this observation of Solomiak and Shmerkin still holds if 1/3 is replaced by any algebraic contraction. And even a slight modification of the argument, we don't even need to require homogeneity. So if you have a system of 3 maps in algebraic contractions, and you know that it is not exponentially separated in infinitely many scales, then it already has exact overlaps.
So what's the point of this corollary, that T can be non-algebraic, but still the conclusion is true?
Yes, T can be what, okay, for 1/3 or for every other algebraic parameters. Okay, for 1/3, you can take whichever real number T you want. And then there are 2 options. Either you have exact overlaps, and then you don't know if you have dimension drop or no. Or the dimension, there is no dimension drop. This dimension formula holds.
By the way, the exact overlaps assumption does not depend on the probabilities, right? Only on
it's only depends on the IFS.
Okay, but the notion of dimension drop depends also on the probabilities,
yes,
the conclusion.
Definitely.
Okay.
And so, as I said, you can. This also holds for general systems of algebraic with algebraic contractions and for systems with 3 maps and the algebraic contractions. On the other hand, this observation of Solomiak and Shmerkin it is not true anymore if you look at systems with algebraic contractions and more than 3 maps. So if one would like to verify the conjecture for such systems, something else needs to be done, which leads me to the following topic, which is systems with algebraic contractions and an arbitrary number of translations. And we're also an arbitrary number of maps. And I mean that the translations are arbitrary real numbers. So in the following theorem, I recently extended the last 2 corollaries. And the theorem verifies the conjecture for systems with algebraic contractions and arbitrary translations, and for systems with any number of maps. And suppose that the theorem says the following: suppose that phi has no exact overlaps, and the contractions are algebraic, and the translations AI are arbitrary real numbers, then there is no dimension drop.
So just to understand, so Hochmann's result requires that also the translations are algebraic, right?
Okay, so yes, he has his main result. It is under this condition of exponential separation and infinitely many scales. And then the first corollary is where all of the parameters are algebraic. And then the second corollary is regarding systems with 3 maps.
Okay.
And
here you only require the contractions to be algebraic, but not the translations, I see.
Yes. So I'll just add a remark that in 2019, last year, Simon Baker constructed the function systems with algebraic contractions, which are not exponentially separated infinitely many scales, but also do not have exact overlaps.
So you want to say that under your assumptions, it does not follow that you have exponential separation?
Yes, so this is what I'm saying, that in Baker examples, which you cannot handle with the previous results, you cannot handle with Hochmann's result, but you can handle with this theorem, which shows that also in this situation, in the situation that you have algebraic contractions, no exact overlap, but also no exponential separation at infinitely many scales, you don't have dimension drop. And also, it is not written here, but in his construction, you can have, and this is related to the question you asked before, you can have these quantities delta n, which measure the closeness of the compositions. They can be arbitrarily small, and you still have the correct dimension. So just observe that by this observation of Solomiak and Shmerkin, such function systems as Baker constructed, they must consist of at least 4 maps. Otherwise, this is not possible. And I'll also add that Chen this year extended this contraction and obtained many such systems, in particular for every algebraic number between 0 and half. He constructs systems, homogeneous systems with these contractions in 4 maps, which has these conditions. And so the bottom line, there are many examples for such systems which are not possible to treat with the previous results, but this result can verify the conjecture. Okay, and I'll say only a few words about the proof. So when the index set, as I said before, when the index set is of size at most 3, the theorem follows by previous methods, so nothing new needs to be done. But when lambda is at least 4, they need to do something new. And the proof involves constructions of certain self-similar measures in higher dimensions. So I defined only self-similar measures on the line, but you can, of course, define self-similar measures also in higher dimensions, and we construct such measures. Given the data of the IFS, we construct such measures for D in this range, for integers D in this range, and then we prove a certain claim that I will not state precisely. We prove it by backward induction for these D's, and we're only interested in the case D equals 1, and this claim that we are proving for the case D equals 1 is precisely the claim we want in the theorem. And the main ingredient in the proof is a result of Hochmann from a different paper in 2015, in which he carries the analysis of the dimension of self-similar measures in higher dimension. But I won't talk about the proof anymore.
But Ariel, can you give us some hint? How do you use the algebraicity of the?
Yes, so it's a the algebraicity is used very, very simply. If you have a integer coefficient polynomial in which you have a nice control over the coefficient, and you have fixed algebraic numbers, and you evaluate the polynomial in this, it's a polynomial of several variables, and you have fixed algebraic numbers, and you evaluate these polynomials at this algebraic number, and you know it is not 0, you have a good lower, you have an estimate on the distance from 0. This is the way, this is the only way algebraicity is used.
So actually you generalize the claim to higher dimensions, and you prove by backward induction, and for D equal to 1, this is, you get what you want.
I'm only care about D equal to 1, but you have to look at higher dimensional measures.
Okay.
Yeah. This idea of constructing self-similar measures in higher dimensions, maybe not precisely in this way, but it appeared before in the literature. It's not the first time it appeared in this proof. But I'll say I won't say any more about this, because I want to reach a recent joint work with Peter Varju regarding homogeneous systems with 3 maps in which the contractions are not necessarily algebraic, and this work is based on the work of Peter Varju and Emmanuel Bouliard regarding Bernoulli convolutions. So now I'll turn to talking about in greater detail about Bernoulli convolutions that I mentioned earlier on, and about their work. So for R between 0 and 1, write phi R for the following function system. It is a homogeneous system which consists with contraction R, which consists of 2 maps, and the translations are plus and minus 1. So this is the most Bernoulli convolutions are the simplest non-trivial situation. And I'll denote by mu R the self-similar measure which corresponds to phi R in the probability vector with equal coordinates, half-half. And this measure is called the Bernoulli convolution with parameter R. And as I said before, it is equal to the law of this random variable, where the plus minus are independent unbiased random variables. And note that in this case, the dimension, the similarity dimension is equal to this, to log 2 divided by log R minus 1, because this is the entropy in this case, and this is the Lyapunov exponent in this case. And so when R is greater than half, the similarity dimension is greater than 1. And additionally note that when R is between, in this interval between 0 and half, the strong separation condition holds, which I recall this is the simple situation in which the images of the attractor does not touch each other. And then we know that there is, in the case of the strong separation condition, we know that there is no dimension drop. So with respect to the exact overlap conjecture regarding to Bernoulli convolution, the interesting part of the problem is showing that the dimension of mu r is equal to 1 for every r in this interval between half and 1, for which the IFS phi r has no exact overlaps. So I'll mention a couple of relevant results. So by the results of Erdos and Garcia, it follows that the dimension of mu r is strictly less than 1 whenever r is in the relevant interval and is an inverse of a Piso number. Recall that a Piso number is a positive algebraic integer, all of whose Galois conjugates are less than 1 in modulus. So these are the only examples we know for which the Bernoulli convolution has dimension less than 1, or even it is not absolutely continuous. On the other hand, a classical result of Boris Solomiak from 95 says that mu r is absolutely continuous for Lebesgue almost every parameter r in the relevant interval, which of course says that almost truly the dimension is equal to 1. And later in his 2012 paper, as a corollary of his main result, Hochmann improved this to dimension 1 outside of a zero-dimensional set. And relying on this result, 2 years later, Shmerkin improved this to absolute continuity outside of a zero-dimensional set. So this is the things this is where the situation stood before the work regarding the conjecture in Bernoulli convolutions until the work of Brouillard and Varjo. And just another remark regarding what it means to have exact overlaps in the context of Bernoulli convolution. So I'll introduce this notation, which will be used also later. Given a positive integer n, I denote by Pn the set of polynomials of degree strictly less than n and coefficients, and these coefficients only plus, minus 1 and 0. And it's not hard to see that the IFS phi r has exact overlaps if and only if r is a root of such a non-zero polynomial. I mean a polynomial with these coefficients. So I'll move talking about the results of Brouillard and Varjo.
So just a moment, just to understand the conjecture. So the conjecture says the following, that if R, the parameter R...
You mean the conjecture in the context of Bernoulli convolution?
In this context, that if the parameter R is not a zero of a plus minus 1, 0 coefficient polynomial, then the dimension of mu R is 1.
In the relevant interval,
In the interval one half.
1/2. Yeah, precisely. Yeah.
Okay, thank you.
So I move on talking about the results of Brouillard and Varjo. So in their first result, they obtain a lower bound for the dimension of mu r for r in the relevant interval under the assumption that r has a large Malur measure. So I'll now define this quantity, which is called the Malur measure, which is kind of measure the complexity of an algebraic number. So let lambda be an algebraic number and let p be its minimal polynomial over z. So these the lambdas are the Galois conjugates of lambda, including lambda itself, and this is the leading coefficient. And then the Malur measure of lambda is denoted by m lambda and defined by this formula. So it is the product of the modulus of the leading coefficients times the modulus of the Galois conjugates, whose modulus is more than 1. And their first result says the following: for every epsilon, there exists m such that the dimension of mu r is at least 1 minus epsilon for every algebraic number in r in the relevant interval whose Malur measure is greater than m. So stated differently, for algebraic numbers in this interval with a large Malur measure, the dimension is close to 1. So they actually prove a stronger result which involves a quantity called the random walk entropy for a certain random walk. But for the purpose of this talk, this version is sufficient, and I wanted to avoid defining the random walk entropy. And move on to the second result. In the second paper regarding Bernoulli convolution, they showed that if R in the relevant interval is such that there is a dimension drop, then at infinitely many scales, R can be approximated extremely well by algebraic numbers R prime in the relevant interval, for which we can control the degree and height. By control of the height, I mean control the Mahler measure. And these approximating parameters also have a dimension drop. So I'll state it precisely. So let R be such that there is a dimension drop. Then for every epsilon and n and big N, there exists n larger than big N and R prime in the relevant interval, such that the following three conditions are satisfied. So first of all, R prime is a root of a non-zero polynomial in Pn. Recall that Pn is the set of polynomials with this degree strictly less than n and the coefficients plus, minus 1 and 0. So we have a good control over the degree and height of the R prime in terms of n. And the dimension of mu R prime is bounded above by the dimension of mu R plus epsilon. And so if epsilon is chosen small enough with respect, if epsilon is chosen small enough with respect to the dimension of mu R, then mu R prime will also have a dimension drop. And the third condition is that R prime approximates R extremely well, much better than exponentially. So there are a number of nice corollaries from this result, which I will not have time to state. For instance, it follows from this result that the dimension of mu pi over 4 is equal to 1. Why is this? Because for such numbers as pi over 4 and many nice transcendental and many other nice transcendental numbers, such an approximation, such a good approximation by controllable by such controllable algebraic numbers is not possible. Okay, I'll move on to talking about various result, who combined his last two results with Breuillard. And
was
Hoffman.
this the first explicit example of a transcendental number with no dimension?
With dimension 1? Yeah. Okay, not specifically, but okay. So I think before I don't remember what came before what, but Vario also has a paper in which he establishes absolute. No, actually, this is for algebraic parameters. So maybe these are the first explicit examples. Probably, if I'm mistaken, then maybe Boris can correct me. But I think that
yes.
You agree that these are the?
I think so. Yes, I think so.
Yeah. In any case, so Vario later combined these last two results that he had with Breuillard and Hochmann's result, which I mentioned from 2012, and proved the following theorem, which says that the dimension of mu R is equal to 1 for every transcendental parameter in the relevant interval. And from this theorem, combined together with Hochmann's corollary regarding systems with algebraic parameters, we get the following very nice result, which says that the exact overlap conjecture holds for the family of Bernoulli convolutions. So let me just add that by extending the methods in the proof of this without much change, it's possible to show that the conjecture holds for homogeneous systems with rational translations in any number of maps. And
does it mean that you know? Does it mean that you know the dimension of mu R for every R?
You mean also R without? No, because okay, so if R is transcendental, you know it's 1, and if R is algebraic, then you need to look at this random walk entropy, which I have not defined, and this will give the dimension. So it's still an interesting. There are still interesting things to look at. But only for algebraic for certain algebraic parameters.
So you know exactly which R give you dimension 1 and which R give you dimension less than 1. But if it's less than 1,
no, because you can have also you can have many exact overlaps, but you will still have dimension 1. It is possible.
Okay. The conjecture is in one direction. The exact overlaps conjecture.
Yeah.
I see.
Yeah. No, it gives necessary and sufficient conditions, but one of the conditions is that if you know that the dimension is strictly less than 1 and you have exact overlaps, then you have dimension drop. But you should include the fact that dimension, you know that the dimension is less than 1.
I see.
So I just remark that the extending this, you can get the conjecture for homogeneous systems with rational translations, and so in the joint paper I have with Vario, we indeed prove this extension because it is required to use it. We use it in our proof. And I'll move on to talking about this. I don't have a lot of time, but I will move on to talking about this result I have with Varjo regarding homogeneous systems with 3 maps. And so as I said, Bernoulli convolution is the first non-trivial, is the simplest non-trivial example of self-similar measures. And now that the conjecture is verified for Bernoulli convolutions, the next simplest thing to consider would be homogeneous systems with 3 maps. And so already in this extension, there are many new problems and many complications that arise. And so from now on, I will refer to this set 0, 1 times R as the parameter space. And for every point RT in the parameter space, we look at the following IFS phi RT, which is a homogeneous IFS with contraction R and 3 maps, and the translations are 0, 1, and T. And we write mu RT for the self-similar measure which corresponds to this IFS and the probability vector with equal weights. And let me just remark that the set of parameters for which these function systems have exact overlaps, in this case, is a countable union. It's not hard to, it's easy to see that in this case, it is a countable union of curves in the parameter space. And this makes a big difference compared to the case of Bernoulli convolution, in which the set of parameters with exact overlaps is the countable set of roots of plus minus 1, 0 polynomials. So this and other stuff creates many new complications. And in the following theorem, Vario and myself have obtained the following result, which extends his second result with Brouillard regarding so it extends the second result regarding the algebraic approximation to this family of measures. And the theorem says the following: let RT be a point in the parameter space such that the function system has no exact overlaps, but there is a dimension drop. So we don't know if such a point exists. It exists if and only if the exact overlap conjecture does not hold for this family of measures. But if such a point exists, then we know to say the following: then for every epsilon and big N, there exists N larger than big N and a point R prime T prime in the parameter space such that the following conditions hold. R prime is a root of a non-zero polynomial of this form for some polynomials P1 up to P4 in Pn. T prime is of the following form for some polynomials P5, P6 in Pn. So again, R prime and T prime, we have a good control over their degree and height in terms of N. And the third condition is that R prime and T prime approximate R and T extremely well in this sense. And the last condition is the dimension of mu R prime T prime is less than the dimension of mu RT plus epsilon. And so if epsilon is small enough, this measure would also have a dimension drop. So this statement, this statement generalizes directly the statement of Brouillard and Various' second result. The proof is definitely not a direct extension. And let me just remark that in the last theorem, it is necessary to assume that the IFS has no exact overlaps. Let me explain why briefly. So indeed, if R is sufficiently small, if it is smaller than this entropy, then there is a dimension drop for the measure mu R1. So mu R1 is the homogeneous measure, corresponds to the homogeneous IFS with contraction R, in which the translations are 0, 1, and 1. So there are exact overlaps caused by words of length 1. And if R is sufficiently small, then it's easy to see that there is a dimension drop. But an approximation as provided in the last theorem is, of course, not always possible. If you look at the number e to the power minus 10, then by results of transcendence measures of such nice transcendental numbers, it's not possible to approximate it that well by these controllable algebraic numbers. So this assumption regarding the absence of exact overlaps is necessary. And I will say a couple of words about the proof. So we use the machinery developed by Brouillard and Various in their second paper. And in order to use this machinery, certain conditions need to be verified. And mostly the proof is devoted to the verification of these conditions, specifically one condition. Now, in Brouillard and Various' second paper, the main difficulty was to establish this machinery, and then the condition it requires are pretty easy to verify in the context of Bernoulli convolution. But here we already have the machinery ready, and we could use it as a black box. But the proof, which is fairly long, is devoted to verifying these conditions. So also the machinery and the conditions it requires, it is too technical for me to describe in this short time. So I can't be more specific, unfortunately. And one more remark, that we actually prove our results for more general two-parameter families, which include other interesting cases. For example, we can treat this family, family of self-similar measures. So here ST is the scaling operator. It takes a real number x and multiplies it by t. And then this family of measures is each of these measures is a convolution of two independent copies of a Bernoulli convolution with parameter r, where one copy is scaled by t. So this is another kind of a natural example we can treat. But I stated everything for the context of the homogeneous system with three maps for simplicity. And I'll mention a couple of corollaries. So how much time do I have left?
4 minutes.
Ah, okay, 4 minutes, it's good. So again, as the last theorem, it verifies the conjecture in this context of the homogeneous system with three maps for many explicit transcendental parameters because of results on transcendence measures. So for instance, if the contraction is any one of these numbers, the conjecture holds for the pair RT for every t. This is because if it would fail, then we would be able to approximate R very well by controllable algebraic numbers, and it's not possible. So this is the first corollary. For the second one, let E be the set of parameters for which the conjecture fails. So this is the set of parameters for which the IFS has no exact overlaps, but there is a dimension drop. And the following result is an easy consequence of our theorem. And it says that E is of house of dimension 0. And let me just mention that in Hochmann's paper, from Hochmann's result, it follows that E is of packing dimension at least 1. And so it is of house of dimension at most 1. And we are able to prove it to house of dimension 0. I'll move on to the last two corollaries, which are more interesting and require more work. So the following corollary verifies the conjecture whenever R is, for every point in the parameter space, whenever R is larger than this constant. So it says that for points in the parameter space where R is larger than this, then and if we know that phi RT has no exact overlaps, then there is no dimension drop. And the proof of this, it uses the last theorem I have with Varju, and then the first result of Broglie-Arden Varju, the one involving the Mahler measure. And the idea of the proof is based on Varju's argument regarding Bernoulli convolution with transcendental parameters, but it also involves many new ideas. And the last corollary that I will not state precisely because I don't have enough time. So by using the similar methods as in the proof of the following corollary, we're able to prove the conjecture in the current setup in the entire parameter space, but we do this conditionally on a suitable generalization of the first result of Broglie-Arden Varju. So there is a natural extension of this first result of Broglie-Arden Varju, which involves the Mahler measure, to the current setup. And we don't know how to prove it, but we know to say that if this natural generalization holds, then the conjecture holds in the entire parameter space. So this is a good direction to make progress with the conjecture, trying to tackle to prove this generalization. So I don't have any more time, so I'll finish.
Thank you very much. Are there any questions? Okay, maybe just a quick question. So in the last results of Varju and yourself with Varju, it was important that somehow the measure was unbiased, right? That you had equal probabilities. But
no, I did it for simplicity, but you can choose any. It doesn't matter at all.
Oh, okay, it doesn't matter. Okay.
Yeah, for any probability.
So for the conjecture, the basic conjecture, what do you expect? Is it true or not?
I think given the, for instance, given the case of algebraic contractions and arbitrary translation, you can have cylinders which are close as you want, but still the conjecture holds. So I think this is a pretty good evidence. Mm-hmm. But I don't know, maybe something weird will happen.
Okay, any other questions? All right, well, thanks very much again.
Thank you.
Thanks. Boris, can we use your hospitality and stay a few more minutes on your
yeah,
Zoom?
Sure. I stop recording now. Okay.
Yeah, gladly. And then